Everyone. First of all, I'd like to thank all the organizers. It means a lot for me to be here, so thank you for having me speak. So at Tanis Levinsky's lab in Columbia, we've developed a new metrological device. It's a molecular lattice clock. It's based on vibrational transitions in the strontium molecule. It's been proposed a while ago. Tanya proposed it about more than 10 years ago, actually. And now it has actually come into operation. On the way, we figured out other physics, that some of it directly applies to what we have to do to get the clock working, but also there have been some sidelines, and we got a very good introduction to this in Robert's talk yesterday, who summarized kind of our collaboration. So we worked with Robert, who's at the University of Warsaw, to give us a lot of guidance, a lot of theoretical predictions about this molecule. So we know where to find our states and how strong our transitions should be. So they figured out, basically that's before I joined the lab, but they figured out the binding potentials really well. And then the lab has also acquired a lot of knowledge about how to control the quantum state, how to do spectroscopy, and how to control some of these transition strengths. Even we've learned how to control them using magnetic fields. We found exotic states as well. Another sideline, which actually doesn't have very much to do with the clock, and turns out to be a very interesting sideline, was a study of ultra-cold chemistry. So it's a very simple chemical reaction that you can do with this strontium molecule. It's sort of the simplest thing you can consider is just photodissociation. And the simple chemical reaction in our system actually shows all the hallmarks of quantum chemistry, as people would have you, as people would present it. So you also saw this in Robert's talk, but basically we can dissociate single quantum states, and we can see things like interference between different paths even in the dissociation process. And you get these really spectacular shapes that we now know and understand thanks to our theory collaborators. Okay, but I won't talk very much about this. I'll just concentrate on the molecular clock and what it took to get it to work. First, a short motivation, which was also covered by Robert. The idea is to go and, well, for at least for one of the projects that we're considering, is to go and map out the ground state potential and just find the resonances. Let's say find all the states, and there's about 63 vibrational states in the ground state potential. And what we can do is we hope we can do is develop a very good understanding of what this potential should be. A much better understanding than any molecule so far, and understand all the old physics that is involved in making up this potential, right? And some of it, although the physics is known, actually calculating exactly the effect on the transitions may not be so trivial. And we hope to actually drive that understanding to the point where we have a model, and then we can subtract the data in some smart way and maybe arrive at some new physics. Okay. One thing that can help us in this is the fact that we have many isotopic pairs of the strontium. So we can do strontium-88 that we're doing right now, but you can also do the other bosons and pairs of bosons of different isotopes, and then that will give you a very good handle of the mass-dependent effects for some of these contributions that you need to understand completely. Okay, so we're somewhat removed from this still, but still, as a motivation further, I want to show this exclusion graph, or maybe not really an exclusion graph, or maybe a search graph, because we'd really like to find something if we went and looked. But this area here shows you a region that is accessible, a phase-space region which is accessible with a 1 Hertz resolution for this strontium clock. And the region, of course, is also something that Robert suggested. Okay, the states, the levels can be affected by a Yukawa correction to the gravitational potential, and this could be a very, very strong correction in very short wavelengths, and no one would know that from previous experiments. And we can actually improve. We have increased sensitivity to some Yukawa physics like this. And the reason why I'm bringing this up again is actually, well, this is sort of the promised region, and we are at 1 Hertz in some respects already. So really not so far from being able to go and do this physics and do this measurement. Okay, so let me dive a little bit into the details. We picked strontium to work with. It has narrow transitions. It has a very broad transition, which is very useful for laser cooling, and it also has the recombination line, which allows also further cooling. But also, there's many molecular potentials, obviously, which are connected to every single bound state here. And the molecular potentials, the states in those potentials that connect to some of these, so let's say this triplet, to this triplet 1 state, actually retain some of the narrow character. And you can use those for spectroscopy as well. Okay, so the strontium molecule itself is a Kunz C molecule. It has unique ground state potential. And as we know from Robert's talk, it's actually pretty well understood also from previous data, but also due to our contribution in spectroscopy that our group has done. The experiment is a typical laser cooling experiment. We start with a MOT, and then an error line MOT on the recombination line, and then we directly load into a one-dimensional optical lattice. There's no further cooling. It's basically cold enough, and the reason why it's a lattice is because we need to be able to do Doppler-free spectroscopy. So really, we're following the footsteps of atomic clocks that are so well characterized, and there's so much written about them. So we simply need to go and repeat those steps for the molecule. To make molecules, we just simply photo-associate. So it turns out that you can just shine resonant light to one of the excited states over here in one of the potentials, and they just happen to have very good overlap. So this state has very good overlap with one of the shallow bound states, and so we start with the shallow bound state that we make this way. Of course, there's molecules created across the potential in a way, but actually the leading contribution, the leading amount or leading population is in a bound state that we know that we want. So we get pretty good signal this way. Then is the business part of the experiment. Spectroscopy. You can do single photon spectroscopy on any one of these narrow states if you would wish to. However, this experiment and the clock is based on a 2-photon transition. So we detune something like 25 megahertz from an excited state, and then we transfer the population to some deeply bound state. In the end, our readout process is just absorption imaging. So we recover these molecules, we dissociate them back into atoms, and image them on a camera. Okay, so we expect that to be a difficult experiment, and there's many technical difficulties, but also there's some more fundamental difficulties, and one of them is the differential polarizability. And actually, the previous talk just gave us a lot of. I almost feel like I got scooped here because there's a lot of details that I'm going to show you, and I had a storyline that I have to follow, and it's very much the same storyline, but please bear with me. So the trick here is how do you account for these inhomogeneous shifts in broadening? Okay, so just in general, two states in the potential will have slightly different polarizabilities, and therefore, if you're in the middle of the trapping potential or the end of the trapping potential, you're going to see different resonant frequencies, right? This means there's essentially thermal broadening. If you measure carefully the line shapes, they're asymmetric like this. And they're shifted, broadened, asymmetric, and actually from this shape you can fit and obtain the temperature of the gas. And this is actually what we do what we use to do thermometry of the molecular system. Okay, so the main thrust of this proposal has been to compensate this shift by introducing a magic lattice. And it's also something that you just saw, but the magic lattice is basically tuning. The idea is to have this deeply bound state. So again, let me just back up for a second. Our clock operates between the shallow state via the 2-photon process here and into the deeply bound state. And we chose this one for technical reasons, but it's actually very close to the bottom of the potential. All of this is to scale here. So this is number 6. So we go from -1, counted from the continuum limit, from the asymptote, down to 6. It turns out that this bottom state actually has a larger polarizability, so it feels a deeper potential, and this is schematically shown here. The potential here in this short dash line forces the state down a little bit further than the upper state, and then what you can do is you can tune your lattice, right? You can tune it and make it magic, essentially connecting this state to some higher excited to some excited state in another potential over here. And if you do it just right, or actually it has to be Bluetooth tuned just a little bit from this state, you can compensate the shift so that both states experience the same light shift. Okay. This is somewhat novel because now we're using a bound-to-bound transition. And okay, so we've done that, right? And so the next piece of data, basically what I'll show you is how you can shift this state around. So you can resolve this motion spectroscopically, just as you saw in the previous talk, and you get these polarizability resonances, or dispersion curves, however you want to call them. But basically they show you, okay, here's the transition, and the scale here is, as you'll see, when I extend the graph, is on the order, just as you saw before, is on the order of 5 to 10 gigahertz. Okay, and so once you hit this magic spot over here, where is the high density of points, with the green line, this is where the polarizability resonance, the polarizabilities cross, and this is the magic wavelength. And what you would expect to see is some background line width actually goes through some resonance and actually goes down to very small values here. The background line width for our parameters is something like 100 kilohertz. By finding the lattice, by finding the magic lattice, we're able to bring this all the way down to about 30 hertz. Okay, so that's orders of magnitude improvement in the quality of the transition. Okay. Incidentally, the slope of this curve right here, the magic detuning, the slope of this curve here basically gives you the required stability for the lattice, for the lattice frequency. Okay, so for the actual frequency of the lattice. So essentially, for clock transition which is stable to within a hertz, you have to have the lattice to be stable to within 10 kilohertz. And the way we do this is we phase lock to our clock laser. So the lattice in this case is actually a clock laser. It's somewhat different from what people normally do, I guess. Now that we have this narrow resonance, we can crank up the intensities of our probes, and we can observe a Rabi oscillation. Okay, and as far as I know, this is the first time somebody's seen a Rabi oscillation across the molecular potential. Is really far, right? They're about 25 terahertz between these two states. And two things become obvious here. There is a decay and a decoherence, and the coherence is just signified by the fact that there's this lift-off, right, over here in the Rabi rate, in the Rabi oscillation. You can only see decoherence this way if it's shorter, if the decoherence time is shorter than the decay time. Okay, and actually this turned out to be some technical issue that we've resolved. We have newer data which I'm not showing you, so please trust me that we have data showing basically decoherence is at least as long as the decay time or longer than that, so we don't see it with our system. So the next step is, of course, to understand the decay and why is it happening. And to us, it was actually it was a surprise. We expected a much smaller decay rate. Okay, so we measure the lifetimes. We can go away from magic, so really far from this resonance, really far from the transition. We observe these curves shown in green here that fit really well to a two-body loss process. Right, we can also go very close to the transition, or close to magic, and this data here, the pink data, is magic, and then you see much decreased lifetimes, and they fit really well, which unfortunately you can't tell from the data, but actually they fit extremely well to single exponentials, meaning that it's a single body loss, and it's most likely is some photon scattering loss. So we try to understand that next. Okay, so what we try to do is look at the scattering rates. We'll look at these loss rates, and we make this following assumption, which I think is a pretty good assumption. So the loss rate there is just equal to the photon scattering rate, and the reason is that this is not a diagonal molecule, so every time when you scatter off of some excited state, actually the likelihood to return to the same vibrational state is nothing, right? So you end up in a different vibrational state, so you stop seeing that molecule. So the curves that you observe basically represent essentially just the photon scattering rate, and the photon scattering rate is just given by this expression, which for our parameters simplifies quite a lot. Okay, here little gamma is the natural lifetime of the excited state, this magic state that we're addressing. Omega is the Rabi rate, and delta is of course the detuning. Omega we can get from fits to the polarizability resonances, and I showed you just one before, but now we have a number of them. So you can get this number really well experimentally determined. And then what you can do is you can go and measure the scattering rate as a function of detuning, and back out gamma from a fit. So in the vicinity of the transition, right? In the vicinity of the transition, where this fast rate, where this fast loss rate is dominating, you get curves like this that fit pretty well to parabolas, right? That's sort of expected here. And from the fit for this parabola, you obtain the single photon scattering rates. Okay, so if you just go naively like this, then you obtain a scattering rate which is actually really high. And it's unexpectedly high. It's orders of magnitude higher than what would have expected from theory. Actually, theory says it should be 2 to 4 kilohertz for a range of different states, and we see in the order of hundreds of kilohertz and even more. Okay, so what's really happening? One thing, so this took us quite a while. We addressed a number of technical issues that we thought could have been causing this. But what we've isolated now, and increasingly seems to be the cause, is maybe actually we're assuming it's a 1 photon scattering rate, which in fact it could be just a 2 photon scattering rate. And so what could be happening is, since you have a really high Rabi rate from this trap, right, which is sitting near resonance, what could be happening is you could be using this this magic state just as a springboard to go to some higher excited state, which could be lossy, right? And so what would be happening in 2 photon process, then the Rabi rate here will be 2 photon Rabi rate, the effective 2 photon Rabi rate. And of course, that gamma would be some other gamma, which is the decay rate. And in principle, this could be a fast decaying excited state. So these numbers could be working out. One thing we can check experimentally is to check the power dependence, because that actually has a different functional form now, because the Rabi rate now shows twice and does the same laser. So the rates should scale like power squared. So the lifetime we expect 1 over p squared dependence, where p is the power of the lattice. And indeed, this is what we see. We see data like this for a couple of different transitions. When we try the third one, and it's slightly different, it's maybe negative 1.6 here instead of negative 2, the dependence. But I would like it to be more clear, but it isn't. And so that's what we get. Actually, in this data is pretty clear. You get this inverse p squared dependence. Then what could be happening? We're trying now to understand, okay, what is this sort of process? Well, there are states everywhere in the molecule. And there's sort of 3 things in my mind that could be happening. One of them is, let's say you're doing a 2 photon scattering off of this intermediate state, and you're hitting another state just accidentally right on the nose in some higher excited state. Well, that could be happening, but then we see similar loss rates no matter what intermediate state we use, no matter what magic state we use. And this 4 different states, and we have 3 more that we've measured, and they're all really lossy. So it's very unlikely that actually we're having some just accidental coincidence here. Another thing that could be happening is we could be landing over here, right? There's an uncountable infinity of states that lives over here in the continuum, and in principle, it could also be essentially just dissociating the molecule. And it's hard to know what strength that is, actually. From talking to our theory friends, it turns out to be very complicated to calculate this reliably. Another thing that could be happening is we could be landing right in here in the high density of states right below the asymptote of some potential. Okay. And what could be happening then is you just can't sit far enough from a transition, and you're just always close to one of them, and you're just scattering. Okay? This is the sort of potentials that we expect are active. It's a number of 1G potentials, and this is one example here of a lattice wavelength. This is 907, I think, is the shortest one that we use. And basically, this is where the first photon ends up, and then this is where the second photon ends up, and it's in some potential and in some other continuum. And it's just some place that is very difficult to contribute to calculate all the contributions from all of these continua and bound states and strengths, transition strengths to our loss rate. But okay, what we can do is we can experimentally cover a number of different. We don't want to extensively cover everything, right? Because we don't have so many lasers. We're using semiconductor laser systems. They're homemade systems, and they're not awfully tunable. So we can cover sort of this range. Okay, so we quickly put together a laser system to probe this asymptote. So the idea here is put a laser, put the lattice where the second photon, so choose a state, choose an intermediate state, so that the second photon lands you in one case right above the asymptote, and in another case right below the asymptote. And so this is sort of trying to say, okay, what's really lossy here? Let's say if we just look at this asymptote, which is a triplet D. If you look at this asymptote, is it that the corresponding continuum is lossy, or is there some dense, or is it just a very dense population of states there that we're addressing? And what we found was sort of similar in the continuum here. So right above the asymptote, we found very similar rates as before, so we can calculate again just to be able to compare some equivalent 1 photon scattering rate, right? Because we don't know what this process is, but we can just say, okay, let's assume it's 1 photon, let's see the scattering rate, just to compare these magic transitions. We get 240 kilohertz, similar to before. If you go right below, it actually grows significantly. So it seems, at least for this pair of states, that there's a significant contribution from this dense set of states there. Okay, it's not a whole lot of data, but I'm pretty sure it's enough to make this sort of general conclusion. Okay, so somewhat preliminary, but basically what we're doing here, again, just to remind you, at really large detunings, we're limited by some two-body loss process, and only in the vicinity we're expecting this photon process, this photon loss. So I'm just limiting this this parabolic fit to the measurement points in the vicinity of the transition. Right. So we don't really know how to overcome this. One good thing about this p-squared power dependence is actually, well, if you go to lower powers, you gain in lifetime. But just to find something that universally works really well, so for this scheme to work with a very long lifetime, somebody needs to tell us, okay, go and look for this special state, and it ends up, or there's maybe some 2 photon scattering rate, which is really low, or maybe there's a different process here that we're overlooking, yeah, that will give us a good idea how to proceed. In the meanwhile, we can make do with what we have, and we can look at sort of, I guess, a list of the things that could be limiting the coherence. Of course, power is one of them. The lattice intensity is one of them, but also things like probability intensity stabilization is the thing that can limit our coherence times, because, you know, as a clock, you're really interested in the coherence times here. Sort of obvious, I guess. And then you can obtain obviously better lasers. You can obtain better cavities that don't drift as much. You can cancel fiber noise, which we've already done. So what's interesting about all these contributions here, a lot of them are technical, that all of them are actually kind of a similar scale. So if you actually want to make something better, if you want to increase the coherence time, you need to be beating back sort of all of these, and a lot of them have been beaten back. So if you consider the probe intensity, for example, what the probes do is they introduce a Stark shift, right? And so the probe itself can broaden your transition because of a Stark shift, but then there's a way around that. Since there's 2 probes, right? It's a Raman process. You can balance their intensity so that the Stark shifts are the same for the bottom and the top state. Okay, and when you do this, then you can change the intensity of the probes by a large fraction here, shown as in this data, with this magic intensity ratio. Okay, so you can keep the intensity ratio the same, and then you can change the overall intensity by a factor of 27 here, and actually the transition doesn't shift around. So we found such an intensity ratio. What needs to happen in the spatial intensity ratio is actually the Rabi rates for the 2 couplings have to be the same, and the Rabi rates you can get independently from a measurement like that, which is just an altered Towns, it's just altered Towns spectroscopy, where the Rabi rate of the coupling laser is just given by the separation between the 2 branches. Okay, and what you would expect from here, from this independent measurement, is this band here, which agrees very well with the spectroscopy data. Okay, so we've also introduced fiber noise cancellations. What else have we done? We have a better cavity in principle. We improved our old one, but anyway, where we are right now is here. We can take line shapes like this for a number of hours. We can take, say, 100 of them for about an hour, and fit spectroscopic line shapes to them, determine the position, and we essentially get a clock. Okay, so self-reference down deviation looks like this. So it is averaging down, and here's 1 Hertz level, and we're essentially there. There's better ways to do this, obviously. Just following the developments in the atomic clocks, what we can do is, instead of taking full line shapes like this, we can just pick 3 points, right? One over here, somewhere far away, to determine the background, and a point here and a point here, just on the side of the line, just to determine the position of the line. And you can implement a servo, which we know how to do, and we've done for other transitions now. So we're technically capable of this, and then you save yourself a lot of measuring time. So what this will do is this will take this curve and just kind of shift it over. And this logarithmic scale is going to shift it over to the left, so you could average down faster. But even at this, with a couple of hours of averaging, you can get down to Hertz, which is, as far as I know, is unprecedented resolution for states across the potential. So you can really get, let's say, the dissociation threshold to Yeah, down to the hertz, or down to a part in negative, down to a part in 10 to the 14. Right. So what we'd like to do next, I guess, is of course characterize the accuracy, because I just showed you something about the precision. We have to look at our error budget, and we're sort of in the process of doing this. We have a few things to investigate. What is our sensitivity to the probability intensities, for example, is one of them. To lattice polarization is just the regular systematics that we have to check. Right. But yeah, what we'd like to do next, in a way, is we can just start scanning this ground state potential, right? And with this, I'd like to thank you for your attention, and all the people who were involved in the project hands-on. Their names are on this picture. Chishi and Con are the senior and the junior graduate students on it. And then Chris came to visit us from MPQ for about a year last year. Right. And of course, our theory collaborators who absolutely we couldn't have done very much without them.
So we have plenty of time for questions.
I'm curious about what's your leading systematic that you have in mind, and because if you want to say this is a good clock, then maybe the advantage of having just as a clock compared to the existing clock.
Right. So okay. So let me start from the back of the question first. We don't ever think that this is going to be a competing clock with the atomic clocks. We're orders of magnitude away from them. It seems like we'll never get so good. One of the reasons is that even if you get a very narrow transition, actually, it's only about over 20-something terahertz, right? The transition that is based on the relative stability takes a pretty big hit by that first. However, it's sensitive to different physics, and that's just due to the more to the different degrees of freedom that are present in the molecule. So we're not really looking to compete and to make a better clock per se. We're trying to make a fairly good clock, as good as we can, just to look for physics that we're sensitive to, and that's based on the fact that we have two massive bodies very close to each other. Well, massive, two atoms, I guess, as massive as atoms are, but they're relatively close to each other, so you can probe things like gravity at the short scale. Leading order systematic, what we kind of expect to be is sort of trivial, actually. It may just be the probability intensity stabilizations, because if one of them shifts a little bit, that shifts your transition due to stark shifts, and with reasonable numbers, without working, I guess intensity is not so easy to stabilize in the first place reliably, and so we may get down to a part in negative 15.
Sorry, can I just comment quickly on this question? I might not completely agree that it has no chance of ever being a atomic clock, and only for the reason that the natural quality factor appears to be extremely high. So for something like Starling clock, it's 10 to the 18. But here we're getting something like 10 to the 26. So if you can get your technology to work, in principle, you can have much higher coherence than in like singlet S triplet P0 kind of clock. But there's a lot of technological challenges.
That's right. Yeah.
What are the prospects for making a competitive ME over MP time variation measurement? And that, for the audience, that would be a probe of dark matter?
Right. I don't know how competitive we are at this point. Maybe Tanya is in a better position to answer.
Well, I would say we are very competitive when it comes to model-independent measurements that don't include the product with the nuclear G factor, which you get when you compare to cesium clocks. So that we could probably do that measurement with this precision. That would be the most competitive. As for NIST-based comparisons based on ratios of optical to, I mean, if you don't worry about the model dependence, then we are a couple orders of magnitude away.
Do you think when you say now, but you could get?
Hopefully, yeah. We have to understand the systematics.
Yeah. Okay.
There's no natural enhancement here, so we're just relying on precision.
Am I right in thinking that if your optical trap has only one wavelength and these zero crossings in the differential polarizability are always going to be close to a resonance,
That's right. So they're fairly weak transitions, and they're always fairly close. So we have to sit between 100 megahertz and a couple of gigahertz away from them.
You had two wavelengths in your optical trap.
If we had two wavelengths in the optical trap.
Put these zeros just somewhere completely away from resonance, I guess.
You saying so stabilized? I guess I have to think about that. It's not obvious to me. There's a lot of gain, but okay, we can discuss. Sorry.
So you have a magic wavelength for your two states, but you're also using this middle state. So what's the influence of that? Do you see? Does it matter if that one shifts in count?
Right. So the middle state. Yeah. Right. Okay. The middle state, which is involved in the two-photon process, right? And so we're far enough detuned away from it, where there's almost no population in it. So we don't.
There's no population in it, but still it has an AC stock shift.
It has an AC stock shift, right? And it's relatively small. I went through an estimate like this. I just seem to forget right now, but right. I mean, I've estimated that effect, right? Because you would imagine that since you're shifting that state, and that's happening, that shift is of course trap dependent, right? So it's coordinate dependent, and what that will do is the effective detuning is going to shift slightly, and that's going to result in slightly different Rabi rates for the two-photon transition across the trap as well. And so that's the decoherence process. We've estimated, and it's lower. I forget the numbers, but it's definitely not a limiting factor by a factor of 10 at least.
Question?
So regarding this discrepancy that you see between the excited state lifetime from theory and your extrapolation from these off-resonance measurements, we see something actually similar in our sodium-cesium tweezer system that seems dependent on the tweezer wavelength. I was just curious, and I might have missed this, do you have a way to measure that directly somehow, like measure the line width of that transition directly under different trap conditions?
We're in the process of trying to do this. Right now, what's funny about this polarizability resonance, that's not proper spectroscopy in a way, because you're actually using the trap. It's not a separate spectroscopy laser that you have so much control on, because it's already very small. And it's very high intensity, it's on all the time. However, now we have two traps because we designed an extra laser system. We're in the process of clearing out exactly this. So if it does have a very large line width, a very large natural line width, like one of those seem to be 10 megahertz, right? Implying we should easily be able to see this in just the direct spectroscopy experiment. And we're doing this exactly now.
All right, so it's lunchtime. We resume at 1:30. And let's thank Stan and all the speakers from this morning.
Thank you.